Hi, my name is Alex. I'm an NASA postdoctoral fellow at the Ames Research Center in California. And today I would like to talk about magnetic fields in galaxies, particularly spiral galaxies, in particular the Whirlpool galaxy M51. Well, we know that magnetic fields are a very important part of star formation. And right now we are starting to think that it may be affecting the whole evolution of galaxies as in the complete scale. This slide shows filamentary cloud. What I'm trying to show here is that magnetic fields are vital for star formation. They remove the excess of angular momentum in the protostellar cores, and in the end collapse and help to shape the filamentary clouds where the stars are being born. Some observations have proved that the magnetic field lines have different directions depending on the density of the ISM, and but that's only inside the filamentary clouds from the Milky Way, and we don't have complete observations until a few years ago about how this may affect the complete scale of a galaxy. Luckily, some very recent simulations are allowing us to start thinking about how the structure of galaxies are modified by switching on and off the magnetic fields. Some results from Van den Boort et al. In 2021 show that the disk may be larger when the magnetic field is different from zero. The black holes can be more massive, and the H1 extended disk can be bigger than without taking into account the magnetic fields. Other simulations, at this from Martinez and Alvarez in 2020, show the opposite, that disks are more concentrated because of magnetic braking. While this is an apparent contradiction, it showed that this is a very complex interlinked scenario where the star formation, the gravity, and the magnetic fields may be affecting the whole galactic evolution takes place. Luckily, we have observations. This slide shows a beautiful picture from NGC 1068 observed by Lopez Rodriguez in 2020, and by using the Sophia Hawk polarimeter. And the main result from this image is that magnetic fields in the are spiral as traced in the molecular gas, despite the complex filamentary patchy structure of the molecular disk. These magnetic field lines are coherent along scales of kiloparsecs. That may start one very simple concept that we don't know of is, can magnetic fields shape galaxies? Well, we know that the magnetic fields cannot affect directly to the stars, but they can affect the kinematics of the molecular gas and before it turns into stars. But this is not exactly new. Magnetic fields are known to be in galaxies in 50 years ago. This earlier observation from 2011 from Fletcher et al. Show that using radio polarimetry observation from the BLA, M51 already had a spiral magnetic field. So what is the difference? Why are we using far infrared or radio observations? Well, radio observations trace the synchrotron polarized gas, which is associated to the diffuse component of the ISM. It's far too diffuse to condense into stars. It's detectable in radio, while the far infrared observations are sensitive to a thermally aligned polarized observation from dust grains, and that traces the molecular clouds, and that gas is ready to form stars. So it'd be like comparing these two different clouds in the atmosphere of the Earth. So and that's only accessible since 2020. So in order to answer if magnetic fields shape galaxies, First, we need to address if all the previous observations and conclusions that have been drawn from the observations on the magnetic field and the diffuse gas are applicable directly to the molecular gas. So is the structure that is traced dependent on wavelength or the tracer? That's something that we need to understand, because if there is a difference on the density of the ISM, then we can start thinking that maybe an influence of the magnetic field as a function of the density and all the phases of the formation of the galaxies. So we got a scientific case. Now we need the data. We use the M51 observation from radio in the galaxy in M51 from BLA and the Effelsberg 100-meter telescope. And we observed with Sophia as part of the legacy program to detect the magnetically aligned task grain thermal far-infrared emission that comes from the molecular clouds. But in the end, what we have is two different maps with directions and every single beam, which mark some kind of magnetic field tracer. How do we compare these magnetic fields? Because it's a whole image. We use just one parameter, the pitch angle, the magnetic pitch angle. We can associate to every single orientation of this field an angle compared to a complete circular field, which is the pitch angle. A very low pitch angle will be closer to a circular field. High pitch angle will be more open, completely radial. So we can do profiles and we can separate between the arms and the interarms. And this is one of the most important profiles I'm going to show, which is the magnetic pitch angle profile. In the y-axis is the magnetic pitch angle. In the x-axis is the distance to the galactic center. And if we show the results from the radio polarized observation from VLA, what we detect is that the radio observations show a very uniform spiral magnetic field, which ranges between 20 and 40 degrees in pitch angle, and is featureless, with the exception of the inner region that is affected by sampling effects. However, if we add the results from the far-infrared observations, we see a very important result in the outskirts. In the inner region, both profiles from far-infrared and in radio, they show the same similar profile, completely compatible. But in the outskirts, the far-infrared magnetic field is distorted. It shows a much tighter spiral pitch angle profile, which makes the spiral arms in far-infrared more tight. Interestingly, this is only visible in the arms. If we go to the interarm regions, we don't see any difference between radio and far-infrared. So now the question is why? What does this mean? We know that the difference between the arm and the interarms is driven because of the density of the galactic disk, also the star formation, but also we see the difference in the outskirts, and we know that M51 is gravitationally interacting with M51. M51A is interacting with M51B. So we know that affects the kinematics of the molecular clouds, that enhance the star formation, and we know that the magnetic fields are interlinked factors between all these two quantities. So we need more clues. But we have already answered one important question. The magnetic field from the diffuse gas is not the same. It's not tracing the same structure than the magnetic field from the molecular gas. So we need more observations in far-infrared, because we don't really know what is the magnetic field structure that the stars are feeling when they are born. So that's the main idea. Now we need to explain what we have been observing. So what we did is to go to the beam by beam observing using ancillary data. We compare the polarized fraction against the velocity dispersion from the molecular gas. And we found out that the polarized fraction decreases very rapidly in far-infrared when we go to high velocity dispersion in the molecular gas. That means that higher density is correlated with higher molecular gas turbulence, and that lowers the polarization fraction in far infrared, but it doesn't affect in radio. As a contrast, if we go to the polarized intensity, not the polarized fraction, but the total polarized intensity, and we compare with this star formation rate, we don't see any dependence with far infrared polarized intensity and the star formation rate, but we see a correlation between radio polarized intensity and the star formation rate. And this is very important because in radio, polarized intensity is a tracer of the strength of the magnetic field, and that may be related to an effect of small scale dynamos. Star formation, higher star formation rate may be correlated with the effect of this small scale dynamos, and maybe increasing the polarized intensity in radio. One of the clues is that in the case of the decrease of the polarized fraction may be affected by, there are two hypotheses for this effect. One, we may be suffering from beam depolarization. Higher turbulent regions may be more complex in morphology, and we may be mixing different directions of the magnetic field. In the end, when you convolve everything with the beam, your polarization fraction decreases. But there's another option that may explain also the independence of the polarized intensity with the star formation rate in far infrared, that is task grain alignment efficiency. According to Redditor-Torps theory on magnetic dust grain alignment, smaller grains may be systematically less aligned than larger dust grains in dense environments. And that would put the limiting factor on the amount of grains that may be emitting polarized intensity in far infrared. And as a consequence, we will observe no correlation with the ISM. So in conclusion, main idea I want you to get from this talk is that the magnetic field in the diffuse gas, as observed by radiopolarized observations, does not share the same structure than the magnetic field traced by the molecular gas in far infrared. So we need to review all the conclusions that we did from the last 50 years in terms of effects of molecular gas and magnetic fields. The star formation, the magnetic fields, and the galaxy mergers are most likely interlinked factors that dominate the outer schedule in 51. So we need more data. We need more observations of galaxies with different configurations, with and without mergers, with stronger spiral arms and more flocculent spiral arms. So we can compare what is the dominant factor that is driving the features that we see in the polarized intensity, polarized fraction, and the pitch angle profiles. All these results are available in the first paper from the Sophia Legacy Program for magnetic fields in galaxies. You're welcome to download the paper. It's available on arXiv and very soon on NAPG. And if you have any questions, I'll be very, very happy to answer by email or in the platform. Thank you very much.